What if the very structure of a sentence held the key to building smarter AI? Today, we're digging into a really powerful mathematical idea that connects the way we create meaning to the future of machine intelligence.
So, let's kick things off with a pretty fundamental question. What does it actually mean for something to have meaning? You know, when linguists and philosophers think about meaning, they often split it into two big categories. On one side, you have the extension. That's all about what something is, right here, right now. And then you have the intension, which is all about what something could be. Okay, so first up is extensional meaning. And honestly, it's the most straightforward way to think about things. It's really just about what something refers to in one single fixed context. You can think of it as the here and now meaning.
So, for example, if you hear the sentence, "The student read the book," from an extensional point of view, all we care about is, well, is it true? In our world, right now, did a specific student, say Alice, read a specific book like Moby Dick? The answer is just a simple yes or no. The meaning gets boiled down to true or false, a 1 or a 0.
Okay, but then you've got intentional meaning. And this is where things get way more interesting. It's about possibilities across all sorts of different contexts. So instead of just one value, the intention is more like a function, a rule that gives you the meaning in any possible context. We're talking alternate realities, future moments, the whole 9 yards. So if we change that sentence just a little to, "The student might read the book," everything changes. The meaning isn't just about our world anymore. Now we have to ask a different question. Is there any possible world, any imaginable scenario where that student reads that book? All of a sudden, the meaning isn't a single point. It's this whole universe of possibilities. And for a long, long time, these two ways of thinking about meaning, they were treated as totally separate things, two parallel tracks in linguistics. But what if they weren't? What if there was a way to see them as just two sides of the same coin? And that's the big question that brings us to our first source.
So a recent paper comes along and proposes something pretty radical. What if we could actually unify these two kinds of meaning? And not just that. What if we could do it using a tool from the world of pure mathematics? It's like trying to build a theory of everything for meaning itself.
The whole goal of this paper is to take both of these models, extensional and intentional, and put them into one single framework to show how they naturally fit together. And the key to unlocking all of this, it's a branch of math called category theory.
Okay, I know what you're thinking. Category theory sounds super intimidating. But don't worry, you don't need a math PhD for this. At its heart, it's really just a language for talking about structures and how they relate to each other. You can picture it as a bunch of dots. Those are the objects, and a bunch of arrows connecting them. Those are the processes that turn one thing into another. It's basically the mathematics of relationships.
All right, so what actually happens when you take this super abstract language of relationships and point it at a very real-world problem, like meaning in human language? Well, what the paper shows is this really elegant three-step journey. First, you start with the two separate models we talked about, extensional and intentional. Then, you apply the lens of category theory, which kind of lets you zoom out and see them from a higher level of abstraction. And when you do that, bam! You discover that one is just a special, kind of collapsed version of the other.
And this is really the key takeaway. The paper proves that a trivial intentional model, that's one where you've basically collapsed all the possibilities down to just a single context, is mathematically the exact same thing as an extensional model. So what does that mean? It means the simple, fixed here and now meaning isn't some separate idea at all. It's just a flattened out version of the richer, multidimensional.
There's a perfect analogy for this. It's like discovering that a photograph is just a single frame from an entire movie. The photograph, that's your extensional meaning. It's static, it's one moment. But the movie it came from, that's the intentional meaning. The whole range of possibilities and contexts. One is literally just a snapshot of the other. Okay, so that's a pretty huge breakthrough for understanding language. But you might be wondering, why does this matter outside of a linguistics department? Well, as we're about to see from our next source, this exact idea, unifying different perspectives, is right at the center of a huge debate about the future of artificial intelligence.
Yeah, because this way of thinking, unifying perspectives, focusing on the underlying structure of relationships, it's not just for linguists anymore. It's now at the very heart of a really passionate and sometimes pretty heated debate about where AI is headed. And you can see just how excited people are about this in a recent discussion on a machine learning forum. One user predicts that in 10 years, the word functor will be as common as tensor is today. And in case you're wondering, a functor is basically a term from category theory. It's one of those arrows we talked about. It's a map between two structures that crucially preserves the relationships inside them.
So is all this excitement justified, or is it just a bunch of hype? Well, when you dig into the debate, it becomes really clear that the community is, well, it's pretty divided.
The whole debate really boils down to two completely opposite views. On one side, you have people who see category theory as a blueprint for the next generation of AI. And on the other side, you've got skeptics who just dismiss it all as unmotivated abstract nonsense. Basically, a fancy new name for ideas we already have.
All right, let's look at the optimistic side first, the bullish view. The people who are all in on this believe category theory could be a total game changer for AI. They see it as a way to create design patterns for building these incredibly complex systems, kind of like having architectural blueprints for software. It gives everyone a common, abstract language to talk about these systems, and maybe, just maybe, it's the key to getting AI out of what one user called its spaghetti code infancy and into a much more mature, disciplined field of engineering.
But of course, the skeptics are nowhere near convinced. As one user, Iron Man, put it pretty bluntly, you won't get anything out of renaming mapping with functor. Their big worry is that this is all just fancy new jargon for concepts that machine learning people already know and use every day, but without adding any real practical value.
And look, this isn't just coming from random people on the internet. Even experts in the field are pumping the brakes, asking the tough questions. Like, what actual practical problems does this super abstract math really solve for machine learning today?
So, when you step back and look at this whole debate, a deeper truth starts to emerge. Whether we're talking about human language or artificial intelligence, maybe the real power of a tool like category theory isn't in the specific answers it gives us. Maybe its real value is in giving us a whole new way to frame our questions, a new blueprint for thinking about complexity itself.
This whole journey, from the meaning of a sentence to the future of AI, it really shows the power of finding the right way to look at a problem. And it leaves us with a pretty big question to chew on. What if the biggest challenges we face today, in something like climate science or economics or even our social systems, aren't really problems of not having enough data, but are actually problems of perspective? What hidden connections, what deep structures are we completely missing just because we don't have the right language to see them yet?